let's understand the effect of latitude on the value of g. That is how the acceleration due to gravity changes with latitude. If we take this as Earth as a solid sphere of uniform mass density, this is North Pole, this is South Pole, and let's say this is moving in this direction with the angular velocity omega. We know angular velocity is the rate at which the angle is subtended at the axis. So for one rotation, if we talk about one rotation, so one rotation is equal to 2 pi radians. So this is 2 pi radian, and corresponding time is 24 hours, that is 24 into, if you multiply 60, that is minutes, into 60, that is seconds. So this much radian per second is the angular velocity of the Earth about its own axis. When we talk about the latitude, latitude is, this is equator. If we take this point P is over here, we join this point P with the center and with this equatorial plane, that is a plane which is passing through the equator. When we join this to the center, this angle alpha, the line makes with the equatorial plane, that is the latitude. As the value of lambda is changing, we are going to study, that is how the value of acceleration due to gravity is going to change over there. A point mass over here, which has a mass m, is being pulled toward the center with a value equal to mg, where g is the acceleration due to gravity, that is 9.81 meter per second square, what we have taken as. In addition to this force, there is one centrifugal force also, that is mr omega square, in the outward direction, because the Earth is rotating about the axis passing the north-south pole. So when it is rotating, so this is an accelerating frame. Rotating frames, they are also accelerating frames, and if you are talking about the accelerating frame, then certainly there is going to be a pseudo force, imaginary force, fictitious force, and that is equal to, we have done in circular motion, that is mv square upon r. We also know that is v is equal to r omega. When we put it over here, so it comes out to be mr upon this thing. So this comes out to be mr omega square, where r is the radius of the circle in which this mass is moving. So this body is moving in this circle of radius r, small r. So this is moving in this circle. So as a result, this experiences centrifugal force, that is mr omega square, in this direction. So as a result, the net force which is experienced by this body is, let's say, mg dash, where we say g dash is the acceleration due to gravity, the net acceleration due to gravity over here, which the body is going to be experiencing. Using parallelogram method of vector addition, we can find the value of mg dash, which is resultant of this force mg and this centrifugal force mr omega square. If you remember what we did in the lectures on vectors, so if there are two forces, there are two vectors, or let's say there are two forces F1 and F2, we join them from tail to tail, we construct a parallelogram, this is parallel to this, this is parallel to this, and let's say the angle between the two is alpha. This diagonal is the resultant. This resultant is given as under root of first vector square, that is F1 square, plus second vector square, plus 2 F1 F2 cos of angle between the two vectors. So same thing we use over here. We have to find this value of mg dash. This and this, they are two vectors. This line and this line, they are parallel. If this angle is lambda, then this plus this is equal to 180. So this angle is going to be 180 minus lambda. So resultant of this and this is, we use once again the same formula. So we say mg dash is equal to mg square, this square plus this square, plus 2ab cos 180 minus alpha. Now cos 180 minus alpha, if you remember, in the first quadrant, all they are positive, sine is positive, tan is positive, in the fourth cos only is positive. So over here, cos 180 minus alpha, that is, it's going to be 1 is cos alpha, over here it is only sine is positive, so minus cos alpha, so minus comes over here. M from here and M from here, they get cancelled. So G dash comes out to be G square plus R square omega square its whole square, that is R square omega 4 minus this thing, it comes like this. When we simplify it, it comes out to be like this. So over here, we can very well find the value of omega. Omega is 2 pi by t. Let's say for one rotation, we know that is omega is, we have just done, that is omega is theta by t. That is omega is angular velocity is equal to theta by t. For one rotation, if you're talking about, so it is 2 pi radian upon total time is in seconds is 24 hours into 60, that is so many minutes into 60 seconds. So this is the time in seconds. So we get the value of omega as 2 pi by t is this much. And the value of r omega square, if we find the value of r omega square by g, that comes out to be 1 by 289. It is 3.4 into 10 to the power minus 3. It is a very small value. Over here we get the value of g dash is equal to g into 1 minus, we have just taken this, we have ignored this because this is once again the square of this. That is, this value is very small, so that's why we can neglect the higher powers of r omega square by g. And over here we say r square omega 4 g square. That is, square of this is going to be even smaller. That's why we have neglected this value. It comes out to 1 minus this value raised to a half. That is square root. So now once again this value is very small. We have used a binomial expansion, that is 1 plus x raised to n. For if x is very small, it is almost approximation is 1 plus nx. So this comes out to be g is 1 minus 1 by 2, 2r omega square cos square lambda by g, and this comes out to be like this. The value of g dash comes out to be g minus r omega square cos square lambda. Now let's say how this value of g dash changes with latitude. As lambda is increasing from here to here, that is over here it is 0, if the particle is over here, if the concerned body is over here, then with this, then the angle it is making with the equatorial plane is 0. If this is 0, that is, this is equal to 1, so this has got a maximum value, so that g dash is the minimum value over here, that is at the equator. As we go from here to here, as the lambda is increasing, so it means 0 to 90, we know that is cos value decreases. As it becomes pi by 2 radian from here to here, if the particle is over here, now with the equatorial plane it is making angle of 90 degree. When it is making angle of 90 degree or pi by 2 radian, so cos lambda that is equal to 0, so g dash becomes equal to g only. That's why g is maximum at the poles and it is minimum at the equator. So from equatorial plane, when we move towards any of the poles, the value of g, that is action due to gravity, that increases. G dash, that is action due to gravity, is minimum at the equatorial plane and it is maximum at the poles. Now if the omega increases, let's say somehow if omega of earth increases, then certainly omega increases, so this value increases. For any particle, be it over here, be it over here, or be it over here, rest of all the things keep it constant, we are just increasing the value of omega. So when omega is increasing, it means this value that is increasing. If this value is increasing, it means this value g, that is constant minus something, this is increasing, so overall this is decreasing. So it means action due to gravity, that is decreasing. So it means for any point, if the earth starts rotating at a higher angular velocity, so obviously the value of action, net acceleration due to gravity over here, that is g dash over here, that will be reducing for any point. But there is no effect of omega on the acceleration due to gravity at the two poles, because over there lambda is going to be equal to 90 degree or pi by 2 radians, so this becomes equal to 0. So whether you reduce it or increase it, this is not going to have any effect on the points on the poles. So generally when we talk about the action due to gravity on the surface of earth, we take it as 9.81 meter per second square. We are not just bothered about what is omega and what is latitude, because the value of this mr omega square or r omega square, that is almost r omega square by g, is very small. So overall the effect of this is very small. If we say r omega square, that is over here, if you put the value of r omega square, even for the equatorial plane, if we talk about where lambda is equal to 0, so g dash is going to be g minus r omega square. R omega square by g is 3.4 into 10 to the power minus 3. So r omega square is going to be, that is g into this thing. So this is almost going to be, even if we take g as 10 meter per second square or 9.8 or 10 meter per second square, so this is going to be 3.4 into 10 to the power minus 2. And for equatorial plane, we are taking lambda as 0, so this comes out to 1. So the value of g dash over here, when we consider the angular velocity of earth and the effect because of angular velocity on the value of action due to gravity, it is very small, because g dash is going to be g minus 3.4 into 10 to the power minus 2, and that is almost equal to the 9.8 minus 0.034, which is almost equal to 9.81 or 9.8 meter per second square only. So very safely we can assume g as 9.8 or 9.81 meter per second square on the surface of earth.